In this video we discuss a merger of rotational vibrational energy to form what we call Ro-Vibrational Spectroscopy. This diagram shows the vibrational and rotational energy levels superimposed upon a harmonic parabolic potential. In this situation, the rotational energy levels are represented in red, the vibrational energy levels are represented in gray. If we take a look at the spacing between the energy levels, we have this arrow here representing the spacing between the rotational energy levels. On the other hand, it's obvious that the spacing between the vibrational energy levels is represented here. And from this, it's clear that the rotational spacing is much less than the vibrational spacing. Now, what that means is that when we look at infrared spectra, the photon energies which are able to excite vibrational energy levels are also more than sufficient to excite rotational energy levels as well. And if we look closely at these spectra, we'll actually see that we actually will get both rotational and vibrational energy levels transitions represented. Basic selection rules for vibrational transitions are as they were when we talked about vibrational spectroscopy earlier. Delta n representing the vibrational quantum number, is equal to +1. In the case of rotational transitions, then the rotational quantum number can change by +1. This represents what we will call the R branch. We'll talk about this later. Delta J may also be -1, and this may seem, at first at least, to be non-intuitive, but we'll come back and talk about that later as well. And there's a situation where delta J can be equal to 0, and this is something called the Q branch. We will find that this does not appear in diatomic molecules, and we will be focusing our discussion on the Ro-Vibrational Spectroscopy of diatomic molecules. Now, if we go back and compare this to rotational spectroscopy, we'll find that just as was the case in rotational microwave spectroscopy, the spacing between the lines in the spectrum within each branch, the P and the R branches, will be equal to 2b, and the spacing between the P and the R branches is equal to 4b, b being the rotational constant. This slide shows rotational and vibrational energy levels and the transitions represented by the red arrows above the actual infrared spectrum of hydrogen chloride. Just to be clear here, this bottom gray line represents the n equals 0, j equals 0 level when the vibrational quantum number is equal to 0 and the rotational quantum number is equal to 0. This line here represents the n equal 1, j equals 0 level when the vibrational quantum number is equal to 1 and the rotational quantum number is equal to 0. Just to be clear, all of these levels here correspond to the n equals 0 vibrational state with different rotational energies. So we have, for example, this particular level right here corresponding to the n equal 0, j equal 5 level, and this one right here corresponds to the n equal 0, j equal 10 level. So that means that the vibrational quantum number is equal to 0, but the rotational quantum number is equal to 10. Up above, we have all the levels corresponding to the n equal 1 vibrational state. In this situation, we'll see that this level here corresponds to vibrational level 1, rotational level 5, and the level above corresponds to vibrational level 1, rotational level 10. So examining the transitions a little bit further, we see that the transition represented by the red arrow here corresponds in the lower spectrum to the transition where n equals 0 to n equal 1, j equals 0 to j equal 1. This transition here corresponds to n equals 0 to n equal 1, j equal 1 to j equal 2. On the other side, we look at the red arrow, the red line here corresponding to n equals 0 to n equal 1, j equal 1 to j equal 0. So you can see the rotational quantum number decreases by 1 on that side. And again, this line here corresponds to vibration level 0 excited to vibration level 1. The rotational quantum number changes from 2 to 1, again decreasing by 1. Let's examine this spectrum in more detail. We'll blow it up so it's a little bit larger so it's easier to see. On the right hand side we see at the higher wave numbers, and you'll notice that the wave numbers are increasing here as we go from left to right. We have the first line corresponds to the 0 to 1 transition. The second line corresponds to the 1 to 2 transition. Then we have the 2 to 3 transition. These are all rotational transitions, so we're talking about all of these on the right side corresponds to transitions from vibrational level 0 to vibrational level 1, accompanied by a rotational transition on top of that. So again, everything here in this diagram corresponds to vibrational level 0 to vibrational level 1. Again, this first line here corresponds to vibration level 0 to vibration level 1, rotation level 0 to rotation level 1. The second line corresponds to vibrational level 0 to vibration level 1, rotational level 1 to rotational level 2, etc. All of these lines on the right side correspond to the R branch of the spectrum because in that case the rotational quantum number is changing by +1. On the left side we have again n equals 0 to n equal 1 transitions, but the rotational level is changing according to this line right here. It goes from j equal 1 to j equals 0. This line is j equal 2 to j equal 1, j equal 3 to j equal 2, so the rotational quantum number is decreasing by 1. This corresponds to what we call the p branch of the spectrum, where delta j in all cases is equal to -1. The gap between the p and the r branches is where the q branch would appear if it was allowed in the case of diatomic molecules. For other molecules, we will indeed see that the q branch does appear. As we noted earlier, the spacing between the lines is equal to 2b, just as was the case for microwave spectra. We see that here in the p branch as well as here in the r branch. So we can use the spacing to calculate the rotational constant b, and of course from the rotational constant b we can calculate the bond length of the molecule. And this is an exercise we'll discuss on a later video. Now, if we look at the Q branch, or excuse me, if we look at these spectra with sufficient resolution, we'll actually see that we have double lines in both the R branch and the P branches, and this is due to the isotopic presence of chlorine-35 and chlorine-37. Their slightly different mass causes shifts in the spectral lines. We'll notice that the chlorine-37 line is lower intensity, and that's because in nature chlorine-35 represents 75% of naturally occurring chlorine, whereas chlorine-37 is roughly 25%. Here is a spectrum of the antisymmetric stretch for carbon dioxide, in which we again see a P branch over here on the right side, and again we'll note that in this case the spectrum frequency wave numbers increase from right to left, and the R branch over here on the left side. Again, from these lines we'll note that the spacing is roughly 2b between the spectral lines. This is something we'll be looking at in more detail in the lab. Now, I did mention that the spacing was roughly 2b, but if we look real closely, we might actually notice that there is some variation in the spacing. In fact, we'll notice that for the P branch, the spacing seems to be getting larger as we go out to lower wave numbers. So the spacing increases as the wave numbers decrease. For the R branch, we'll actually notice that the same kind of trend, that the spacing actually, as we go to higher wave numbers, the spacing actually is decreasing. So what's that all about? Well, again, we'll talk about this in more detail in the lab, but it's due to something called rotational vibrational coupling. And this is due to the fact that the rotational constant actually depends on the vibrational energy. That's because the rotational constant is dependent on the moment of inertia, and the moment of inertia depends on the square of the bond length. As the square of the bond length increases, the square of the bond length will increase as n increases, and that's due to the vibration, of course, changing the bond length as the vibration stretches, as the bond stretches during the vibration. Of course, the moment of inertia will increase. As the bond shrinks during the vibration, the moment of inertia will decrease. So we will note again that the mean square bond length actually goes up as the quantum number, the vibrational quantum number, goes up. And if the moment of inertia goes up as the n quantum number goes up, that means that the rotational constant actually decreases as n, the vibrational quantum number, increases. And as a result of this, the R branch lines get closer together as the J transition increases as we go to higher frequencies, and the P branch lines get farther apart as J increases, meaning as we go to lower frequencies, which is what we observed on the last slide. The effective rotational quantum number depends on, as we noted above, on the quantum level n, and the equation that we have here shows that effective change. And again, we'll note, because of this second term here, that the rotational constant decreases as n increases. This constant alpha is referred to as the vibration rotation coupling constant. Very creative name, that. This ends our discussion of Ro-Vibrational Spectroscopy. We'll follow this up with a few videos that run through some computational details.